the most of human history, fear has been external. Predators, disease, famine, war. Even the most terrifying ideas had a boundary. Death was the final line. Whatever happened after that, if anything, was no longer part of lived experience. Modern physics quietly challenges that assumption. Not through belief or speculation, but through interpretations of equations that already work. Some of the most unsettling ideas in science are not about destruction, invasion, or extinction. They are about persistence, about what consciousness is allowed to escape. This is a list of 10 such ideas. Each is debated. None are fringe. And each becomes disturbing not because it is dramatic, but because it removes something humans rely on to feel safe. The first theory we will cover tonight comes from quantum mechanics and one of its most serious interpretations, the many worlds interpretation. At the quantum level, reality does not behave like a system that selects a single outcome. Instead, every outcome permitted by the equations occurs. When a quantum event takes place, such as a particle decaying or remaining stable, the universe does not choose between them. Both outcomes happen. Reality splits into separate branches, each containing a complete version of the universe in which that outcome occurred. Most of these branches differ only in microscopic ways. A photon scatters at a slightly different angle. An electron tunnels or does not. These differences accumulate quietly and remain invisible at the scale of everyday life. But occasionally, a branching event involves something far more consequential. Survival. In one branch, an accident proves fatal. In another, the body lands differently. In one branch, a heart stops. In another, it does not. From an external perspective, all of these branches are equally real. From the internal perspective of consciousness, something deeply asymmetric occurs. Awareness only continues in branches where the brain remains capable of experience. There is no perception of the branches in which death occurs, because awareness does not exist there. The observer never finds themselves in a reality where their own experience has ended. This is not because death fails to happen. It is because experience cannot register its own absence. This asymmetry leads to the idea known as quantum immortality. Subjectively, an observer never experiences their own death. No matter how extreme the danger, as long as there exists even one branch of reality where neural activity continues, consciousness persists in that branch. All other branches still exist. Bodies still fail. Friends still grieve. But the version capable of awareness is always the one that survives. From the inside, this survival does not feel miraculous. It feels ordinary. The car swerves. The fall is broken. The diagnosis is revised. The rare outcome occurs again and again. Not because it is likely, but because it is the only outcome that can be experienced. Probability does not reward the observer. It filters them. It is important to understand what this theory does not claim. Quantum immortality does not imply invulnerability. It does not prevent injury, disease, aging, or deterioration. It does not promise eternal youth or comfort. It removes only one thing: the hard stop of subjective experience. As long as survival is not strictly impossible, as long as the probability of continued neural function is not exactly zero, awareness continues. This creates a subtle but unsettling shift in how survival is understood. Life no longer ends, because it is unlikely to continue. It ends only when continuation becomes impossible, and quantum mechanics, by its nature, almost never assigns a probability of absolute zero. The deeper consequence of quantum immortality only becomes clear when time is allowed to stretch forward. In the early stages of life, the surviving branches look almost identical to ordinary reality. Injuries heal. Illnesses resolve. The world feels familiar. But as years pass, continued awareness increasingly depends on events that are not just unlikely, but extraordinary. Survival begins to rely on rare biological resilience, experimental medical interventions, or improbable coincidences that occur only in a tiny fraction of possible branches. From the outside, this looks exactly like ordinary mortality. Almost every version of the individual dies at a statistically normal time. Friends observe decline, death certificates are written, funerals take place. History closes the book. But from the inside, there is no such closure. Consciousness continues only along the narrowing path where neural activity persists. This creates a growing divergence between subjective experience and objective history. The world that awareness inhabits becomes increasingly atypical compared to the world most versions experienced. This is where the theory becomes psychologically disturbing rather than merely strange. Quantum immortality does not imply a long, healthy life. It implies persistence under worsening conditions. Survival does not mean thriving. It means not having reached absolute impossibility. As time goes on, the branches that support awareness are increasingly constrained. Perhaps cognition is maintained through artificial support. Perhaps awareness continues with severe physical or neurological impairment. Perhaps survival depends on technological environments that bear little resemblance to ordinary human life. The crucial point is that consciousness does not choose these outcomes. There is no preference or agency involved. The observer does not move toward comfort or meaning. They are carried forward automatically by probability itself. Wherever awareness can still exist, that is where experience continues. All other branches, however numerous, contain no observer to notice their conclusion. This reframes death in a profoundly unsettling way. Death ceases to be an endpoint. It becomes a sorting process. The versions that die do so cleanly and permanently, but they're never the ones asking what happened next. The only perspective that remains is the one that did not die. From that perspective, survival feels inevitable, even as the conditions required for survival become increasingly extreme. Quantum immortality also dissolves the comforting symmetry between observer and world. Normally, we assume that our experience aligns with external reality. When others see us die, we assume we would experience the same event. This theory breaks that symmetry. The external world moves on without us. The internal world never encounters the ending. The two histories diverge irreversibly. The horror of this idea lies not in endless life, but in endless continuation, without release. Death is no longer a boundary that guarantees rest. It is something that always happens elsewhere. Survival becomes a mechanical consequence of how observation works in a branching universe, not a reward for resilience or meaning. If the many worlds interpretation is correct, consciousness is not allowed to experience its own absence. As long as there exists even a vanishingly small path forward, awareness follows it. And the longer time goes on, the stranger that path becomes. The second theory we will cover tonight comes not from quantum mechanics directly, but from thermodynamics, specifically the mathematics of entropy and probability. It begins with an assumption so ordinary, it is rarely questioned. But the universe we observe is the result of a long, continuous history. A beginning, an expansion, stars forming, planets cooling, life evolving, and eventually minds capable of wondering how it all began. Modern physics quietly suggests that this assumption may be statistically backward. Entropy is a measure of disorder, or more precisely, a measure of how many microscopic arrangements correspond to a given macroscopic state. Systems naturally move towards states with higher entropy because there are vastly more ways for disorder to exist than order. A hot cup of coffee cools. A structure decays. Energy spreads out. This is not a tendency. It is a mathematical inevitability. Over time, the universe drifts towards states that require the least information to describe. According to standard cosmology, the universe began in an extraordinarily low entropy state. Matter and energy were arranged with extreme precision. As time moved forward, entropy increased, allowing stars, galaxies, and eventually life to emerge. This picture already contains a deep mystery. Low entropy beginnings are not forbidden by physics, but they are profoundly unlikely. The universe appears to have started in an incredibly special configuration for reasons we do not understand. Now extend this reasoning forward rather than backward. If the universe continues for a very long time, entropy continues to rise. Stars burn out. Black holes evaporate. Matter thins. Eventually, the universe reaches a close to uniform equilibrium known as heat death. In this state, nothing large or complex should happen. The universe becomes cold, dark, and mostly empty. But quantum mechanics introduces a complication. Even in a vacuum, fluctuations occur. Energy jitters. Particles appear briefly and vanish. Normally, these fluctuations are tiny. But given enough time, extremely unlikely fluctuations become inevitable. Over infinite time, random fluctuations will produce not just particles, but structures. A molecule, a cell, and eventually, something far more unsettling. A functioning human brain, fully formed, with neurons arranged in a way that supports consciousness, with electrical activity corresponding to thoughts, with memories encoded physically in neural structure. This hypothetical observer is known as a Boltzmann brain. The disturbing aspect of Boltzmann brains is not that they are strange. It is that they are statistically favored. Creating an entire universe with billions of galaxies and a coherent past requires an extraordinarily low entropy starting point. Creating a single brain requires far less order. From a probabilistic standpoint, it is vastly easier for the universe to fluctuate a lone observer into existence than to fluctuate an entire cosmos, capable of producing observers naturally. If the universe lasts long enough, Boltzmann brains should vastly outnumber ordinary observers. That means that, statistically, the typical conscious experience in such a universe is not a being who evolved on a planet with a long history, but a disembodied brain that forms spontaneously and exists only briefly before dissolving back into chaos. Here is where the theory becomes genuinely unsettling. A Boltzmann brain would not know it was one. Consciousness does not require a real past. It requires structure in the present. If the fluctuation assembles a brain with the right physical configuration, it will experience memories. Childhood, relationships, a world with rules and continuity. Those memories would feel exactly as real as yours do now. They would not be vague or dreamlike. They would feel grounded, detailed, and emotionally charged. The environment perceived by a Boltzmann brain does not need to exist externally. The fluctuation could include sensory input patterns that create the illusion of a surrounding world. Or the brain could hallucinate that world internally. From the inside, there is no experiment that distinguishes between a real external history and a fabricated one. Every attempt to verify reality relies on memory, perception, and inference, all of which could be part of the fluctuation itself. This leads to a deeply destabilizing conclusion. If Boltzmann brains dominate the population of observers, then it becomes statistically more likely that you are a Boltzmann brain than a naturally evolved human. The fact that your experiences feel coherent does not help. Boltzmann brains would also experience coherence. The fact that your memories are detailed does not help. Those memories are just physical states of neurons, and physical states can arise randomly. This creates a paradox known as cognitive instability. If our cosmological theories predict that most observers are Boltzmann brains, then we should doubt our own observations. But if we doubt our observations, we should doubt the theories built from those observations. The theory undermines the evidence that supports it. Physics begins to saw off the branch it is standing on. Because of this, many physicists argue that any correct theory of the universe must somehow avoid producing Boltzmann brains in large numbers. This is not because there is evidence against them, but because accepting them destabilizes the entire notion of scientific knowledge. Some propose that the universe must end. Others suggest vacuum decay or cosmic collapse. In a subtle way, new physics is invented not because data demands it, but because the alternative implies that we are probably hallucinations. The existential horror of Boltzmann brains lies in the loss of narrative. Humans are story-based creatures. Meaning depends on continuity, a past that led to this moment, and a future that flows from it. The Boltzmann brain hypothesis dissolves that structure. Your memories may not correspond to real events. Your sense of identity may be a temporary configuration. The people you care about may not exist outside your experience. Unlike other threats, there is no survival strategy here. You cannot hide. You cannot escape. You cannot disprove it. Every piece of evidence you might use is already part of the system being questioned. Reality does not collapse violently. It quietly becomes unreliable. If quantum immortality removes the certainty of death as an ending, Boltzmann brains remove the certainty that there was ever a beginning worth remembering. Consciousness becomes a statistical accident, flickering briefly in an ocean of entropy, convinced it belongs to a world that may never have existed at all. The third theory we will cover tonight does not describe destruction, extinction, or illusion. It attacks something far more fundamental: agency. The assumption that choices are made freely, that experiments are conducted independently, and that questions can be asked of nature without the answers already being fixed. Superdeterminism is a serious, if deeply uncomfortable, proposal in the foundations of physics that suggests this assumption may be false. To understand why superdeterminism exists at all, it helps to begin with one of the most important discoveries in modern physics: quantum entanglement. When two particles interact and then separate, quantum mechanics predicts that their properties can remain linked, even across vast distances. Measure one particle, and the state of the other is instantly correlated, regardless of how far apart they are. This phenomenon has been confirmed repeatedly in experiments. Albert Einstein famously disliked this implication. He believed that physics should respect realism, the idea that physical properties exist independently of observation, and locality, the idea that information cannot travel faster than light. To preserve these principles, Einstein suggested that quantum mechanics must be incomplete. He proposed that particles carry hidden variables, unseen parameters that determine outcomes in advance. In the 1960s, physicist John Bell showed that this idea could be tested. Bell derived an inequality, a mathematical limit that any theory based on local hidden variables must obey. If experiments violated this limit, then no theory that preserves both realism and locality could be correct. Over decades, increasingly precise experiments were performed. They consistently violated Bell's inequality, In 2022, this result was recognized with a Nobel Prize. Nature does not behave in a way that preserves all of our intuitive assumptions. At face value, this leaves only a few options. One option is that information travels faster than light, violating locality. Another is that particles do not have definite properties until they are measured, abandoning realism. Most physicists accept some version of the second option. The world is not fully real until it is observed. Measurement plays a fundamental role in bringing facts into existence. Superdeterminism offers a third option. It preserves both realism and locality, but at a severe cost. It rejects the hidden assumption underlying Bell's theorem, the assumption of statistical independence. This assumption states that the choice of measurement settings in an experiment is independent of the physical state of the particles being measured. In simple terms, it assumes that the experimenter is free to choose what to measure. Superdeterminism denies this. It proposes that the universe is so deeply correlated, but the state of the particles and the choices of the experimenter share a common cause in the past. The settings of the measuring devices, the thoughts of the scientists, and the properties of the particles were all fixed together from the beginning of the universe. There is no randomness. There is no independence. Everything unfolds as a single, consistent trajectory. Under this view, Bell's inequality is violated not because particles communicate faster than light, and not because reality is created by observation, but because the universe never allowed the experiment to be set up in a way that would reveal otherwise. The correlations are built in. The outcome was guaranteed before the experiment was conceived. The apparent freedom of choice was an illusion. This is where the theory becomes psychologically disturbing. Superdeterminism does not merely say that events are determined by prior causes, a position many people already accept. It says that the feeling of choosing is itself part of the determined system. Every decision, every doubt, every attempt to test the theory is already accounted for in the initial conditions of the universe. The sense of agency is a byproduct, not a driver. This has profound implications for science itself. The scientific method relies on the idea that nature can be interrogated. An experiment is designed, a question is asked, and the universe responds. Under superdeterminism, no question is ever truly asked. The experiment and the outcome are two parts of the same predetermined script. The appearance of discovery replaces discovery itself. This does not require conspiracy or intention. There is no cosmic mind manipulating outcomes. The universe does not need to deceive. It simply unfolds according to its initial state. The laws of physics we uncover are not chosen from many possibilities. They are the only ones we were ever able to uncover. Alternative experiments that might have revealed different structures were never physically possible, even if they felt possible subjectively. This reframes the concept of free will at a physical level. Thoughts arise. Decisions feel real. Actions follow. But none of these alter the trajectory of the universe. They are expressions of it. The distinction between observer and system dissolves. The scientist is not standing outside reality, probing it. The scientist is part of the mechanism producing the result. One of the most unsettling consequences of superdeterminism is that it undermines the meaning of doubt. Normally, skepticism is a safeguard. Questioning assumptions protects against error. Under superdeterminism, skepticism itself is predetermined. Agreement and disagreement are equally scripted. The act of rejecting the theory does not stand outside it. It confirms it. Critics often argue that superdeterminism is unfalsifiable, and that is precisely what makes it disturbing. A theory that explains every possible outcome also explains away the possibility of testing it. There is no experiment that can be performed independently of the conditions that guarantee its result. Physics becomes observationally closed. Some physicists argue that this makes the theory unscientific. Others argue that nature is not obligated to be testable in ways that comfort human intuition. If superdeterminism is true, then the discomfort itself is irrelevant. The universe does not need to grant epistemic freedom. The existential weight of this idea lies in what it removes. Not life, not consciousness, not even meaning in a poetic sense. It removes authorship. Experiences still occur. Emotions still feel real, but the sense that choices steer reality dissolves. The future does not respond to intention. It unfolds regardless of it. In such a universe, the feeling of participation becomes cosmetic. Awareness observes decisions being made, but does not make them. The story continues, but the narrator has no influence over the plot. Reality becomes a completed structure being revealed frame by frame, rather than a space of open possibilities. If quantum immortality traps consciousness in survival and Boltzmann brains destabilize the past, superdeterminism closes the remaining door, the idea that agency provides an escape. Under this theory, even the act of searching for meaning is part of a trajectory that was never alterable. The universe does not merely limit freedom. It never contained it at all. The fourth theory we will cover tonight attempts to explain one of the most unsettling observations in modern science: the silence of the universe. When astronomers look out into space, they see hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars have planets. Many of those planets likely have conditions suitable for life. And yet, when we listen for signs of intelligence, we hear nothing. No signals, no structures, no evidence of cosmic neighbors. This contradiction is known as the Fermi paradox. The dark forest theory proposes that the silence is not accidental. It is deliberate. The dark forest theory begins with two assumptions that are difficult to reject. First, survival is the primary objective of any civilization. Second, resources in the universe are finite, even if vast. From these two premises, a grim logic emerges. If intelligent civilizations exist, they exist in a universe where they cannot know the intentions of others. Communication across interstellar distances takes years, centuries, or millennia. By the time a message is received, the sender may already have changed beyond recognition. Technology advances unpredictably. A civilization that is harmless today may become overwhelmingly powerful tomorrow. This creates what theorists call a chain of suspicion. When one civilization becomes aware of another, it cannot assume benevolence. Even if the other civilization appears peaceful, there is no guarantee it will remain so. Even if it remains peaceful, it still consumes resources and occupies territory that could one day be needed for survival. Waiting to gather more information is itself a risk. In an environment where a single mistake can mean extinction, caution dominates morality. In this framework, the rational strategy is silence. To reveal your location is to gamble your existence on the goodwill and restraint of an unknown intelligence. To broadcast signals is to announce yourself as a potential future threat. The safest move is to observe quietly, remain hidden, and avoid drawing attention. Civilizations that fail to do this do not leave descendants. They are removed from the cosmic landscape before they can spread. The dark forest metaphor illustrates this logic. Imagine a vast forest at night, filled with armed hunters. Each hunter moves silently, aware that others are nearby but unable to see them. If one hunter makes a noise, they reveal their position. The rational response from any other hunter is to eliminate the source of the noise immediately, before it becomes a danger. In this forest, kindness is not rewarded. Silence is survival. Applied to the universe, this suggests that space is not empty. It is full of watchers. Civilizations that endure are those that remain undetectable. Those that broadcast, expand recklessly, or attempt open communication are selected against. Over cosmic timescales, the only voices left are the ones that never spoke. This casts human behavior in an unsettling light. For over a century, humanity has been transmitting radio signals into space. We have sent deliberate messages advertising our location. We have placed maps of our solar system on spacecraft. From the perspective of the dark forest, this is not exploration. It is exposure. To a hostile or even cautious civilization, these signals do not look like greetings. They look like warning signs, evidence of a rapidly advancing species that has not yet learned to hide. The theory does not require malevolence. It does not assume aliens are cruel or aggressive by nature. It assumes only that they are rational under conditions of uncertainty. Even a civilization that values cooperation faces a dilemma. Revealing itself risks annihilation. Remaining silent preserves survival. Over time, natural selection favors paranoia. One of the most disturbing implications of the dark forest theory is that contact, if it occurs, is unlikely to be friendly. The first encounter would not involve conversation or negotiation. It would involve neutralization. Not out of hatred, but out of risk management. At interstellar scales, preemptive action is safer than dialogue. Misjudging intentions even once could erase an entire lineage. The silence of the universe, under this view, is not comforting. It is tense. Every civilization listens. None respond. Signals are monitored, catalogued, and evaluated. Action is delayed not out of mercy, but out of caution. And when action comes, it comes decisively. This theory also explains why we see no visible signs of galactic engineering. No obvious megastructures. No large-scale manipulation of stars. Such activity would announce presence across vast distances. A civilization that survives learns to minimize its footprint. Expansion is quiet. Energy use is concealed. Growth occurs in ways that are difficult to detect. The existential weight of the dark forest theory lies in what it suggests about our future. If it is correct, then the moment a civilization becomes visible is the moment it becomes vulnerable. Technological adolescence is the most dangerous phase. Too advanced to remain unnoticed, but not advanced enough to defend against unknown threats. The universe does not reward curiosity. It rewards discretion. Unlike other cosmic threats, the dark forest does not promise sudden destruction. It promises prolonged tension. A universe where silence is not emptiness, but restraint. Where the absence of voices is evidence of danger, not peace. Where the greatest mistake a civilization can make is to assume that no answer means no one is listening. If the earlier theories remove escape, memory, and agency, the dark forest removes trust. It suggests that the universe is not a shared home waiting to be explored, but a crowded territory where survival depends on remaining unseen. The stars are not quiet because they are empty. They are quiet because anything that speaks does not speak for long. The fifth theory we will cover tonight builds directly on the same silence that gave rise to the dark forest, but it reaches a very different conclusion. Instead of assuming the universe is quiet because civilizations are hiding, the Grabby aliens model suggests the universe is quiet because it is already in the process of being taken. This idea comes from formal modeling rather than speculation, using economics, game theory, and cosmology to ask a simple question. If intelligent life appears at different times, and some civilizations choose to expand aggressively, what would the universe actually look like from the inside? The model begins with a distinction between two broad types of civilizations. Most are passive. They develop technology, perhaps explore their local system, and eventually stagnate, collapse, or turn inward. A small minority behave differently. These are the Grabby civilizations. They expand rapidly, converting matter into energy, computation, or infrastructure. They do not wait. They do not optimize for harmony. They optimize for reach. Expansion, in this model, does not require malice. It requires only capability and incentive. If a civilization can expand at a significant fraction of the speed of light, even slowly by human standards, the mathematics become overwhelming. Expansion fronts move outward in all directions, forming growing bubbles that consume usable matter as they go. Given enough time, these bubbles collide and fill the available space. What makes this model disturbing is its timescale. Even with conservative assumptions, a single expansionist civilization could saturate an entire galaxy in a few million years. In cosmic terms, this is negligible. The universe is more than 13 billion years old. If Grabby civilizations arise even rarely, their effects should already dominate the observable universe. So why do we not see them? Why does the sky still look empty? The Grabby aliens model answers this by pointing to selection bias. We observe the universe from a location that has not yet been overtaken. That is the only kind of location from which observation is possible. If we were inside an expanding civilization's domain, the sky would not look empty. It would look engineered. The fact that we see emptiness does not mean expansion is absent. It means we are early, or we are in a remaining gap. The analogy often used is biological. Imagine mold growing in a petri dish. The mold begins at a few random points and expands outward in circles. Over time, the circles grow and eventually merge, covering the dish. If a bacterium happens to evolve in one of the last untouched regions, it would look around and see empty space. It would conclude that no mold exists. But that conclusion would be false. The emptiness would simply reflect its position in time and space. According to the model, humanity appears unusually early in the history of the universe. This is not a coincidence. Later in cosmic history, there will be fewer untouched regions where new civilizations can arise. The fact that we exist at all suggests that the window for independent emergence is limited. The universe may already be partitioned into expanding domains, most of which lie beyond our current observational horizon. This leads to a deeply unsettling implication. The absence of visible expansion does not mean safety. It means delay. Light travels at a finite speed. The regions of space we can observe are limited by how long light has had to reach us. An expansion front moving toward us at a significant fraction of the speed of light could already exist beyond our horizon. Its effects would be invisible until they arrive, at which point there would be no warning. Unlike the dark forest, this model does not rely on fear, paranoia, or preemptive violence. It relies on inevitability. Expansion is simply what some successful strategies look like when scaled to cosmic time. A Grabby civilization does not need to hunt others. It only needs to expand efficiently. Any civilization that lies in its path is overwritten, absorbed, or rendered irrelevant by default. The model also reframes the idea of cosmic competition. It is not that civilizations fight for territory. It is that territory disappears. Matter is converted. Stars are dismantled. Energy flows are redirected. From the inside of such a domain, this may look like prosperity, computation, or stability. From the outside, it looks like nothing at all. The night sky remains dark because the energy is being used efficiently rather than wasted as visible light. This explains why we see no obvious megastructures. A truly advanced civilization minimizes waste. It does not broadcast its presence. It does not leave easily detectable signatures. It optimizes silently. Expansion does not need to be loud to be effective. For humanity, the implications are stark. If the Grabby aliens model is correct, then our apparent freedom is temporary. We are not living in an eternal empty universe waiting to be explored. We are living in the brief interval before contact, not necessarily with another civilization, but with an expanding boundary that does not need to recognize us, to displace us. There is no negotiation with an expansion front, no warning signal, no diplomatic channel. By the time the evidence arrives, the process is already complete. From our perspective, the universe changes abruptly. From the perspective of the expansion, nothing unusual happens at all. The psychological horror of this theory lies in how it reframes hope. Exploration, curiosity, and growth are not safeguards. They are races. The universe is not a shared commons waiting for cooperation. It is a landscape being carved up by whoever started first and moved fastest. We are not late because we are unlucky. We are early because later may not exist. If the dark forest suggests that silence is intentional, the Grabby aliens model suggests that silence is temporary. The universe is quiet not because nothing is happening, but because the processes that matter operate beyond our current view. We are not alone in an empty cosmos. We are alone in a shrinking gap. The sixth theory we will cover tonight does not involve aliens, intelligence, or observation. It does not care whether life exists at all. It concerns the stability of reality itself. False vacuum decay is a consequence of quantum field theory and particle physics, and it suggests that the universe may be sitting in a temporary configuration that could collapse without warning, erasing the laws of nature as we know them. To understand this idea, it helps to think in terms of energy. In physics, systems naturally move toward states of lower energy. A ball rolls downhill until it reaches the lowest point in a valley. Once it reaches the bottom, it stays there. This is a stable state. The assumption most people make, often without realizing it, is that the universe itself is already in such a lowest energy configuration. That the rules governing particles, forces, and matter are fixed because they have nowhere else to go. Modern particle physics does not guarantee this. Calculations involving the Higgs field, the field responsible for giving particles their mass, suggest that our universe may not be in the lowest possible energy state. Instead, it may be in a metastable state, a false vacuum. This is like a ball resting in a shallow dip halfway down a hillside. It appears stable. It can remain there for an extremely long time, but it is not truly at rest. A deeper valley exists below. As long as the ball remains in the shallow dip, nothing dramatic happens. The system behaves predictably. This is the state our universe appears to be in now. The laws of physics function consistently. Atoms hold together. Chemistry works. Stars burn. Life exists. The quantum mechanics allows something classical physics forbids: tunneling. A system does not need to climb over an energy barrier to reach a lower state. It can pass through it. If a quantum tunneling event were to occur in the Higgs field, Even at a single microscopic point in space, the universe could transition to a lower energy vacuum state. This transition would not be gradual. It would not be explosive in the conventional sense. It would be absolute. A bubble of true vacuum would form, inside which the values of fundamental constants would be different. This bubble would expand at the speed of light, not slower, not faster, exactly at the cosmic speed limit. That detail matters, because information also travels at the speed of light. There would be no warning, no visible approach, no time to react. The moment the information that the bubble exists reaches you is the moment the bubble arrives. Inside the bubble, the laws of physics as we know them would no longer apply. Particle masses would change. Forces could weaken, strengthen, or disappear entirely. Atoms might not be able to exist. Chemistry could become impossible. Protons might decay. The structures that make up matter, stars, planets, and bodies, would disintegrate instantly. This is not destruction in the usual sense. It is not fire or impact. It is erasure at the level of law. The unsettling aspect of false vacuum decay is that it does not target life. It targets consistency. Everything depends on the specific values of physical constants. Change them slightly, and stars cannot form. Change them more, and matter cannot exist. Life is not fragile because biology is delicate. Life is fragile because it sits on an extremely narrow range of physical parameters. The probability of vacuum decay is believed to be extremely small, but it is not zero, and that distinction matters. A probability of zero means something is forbidden. A probability greater than zero means something can happen. Given enough time, rare events become inevitable. The universe is already more than 13 billion years old. It may last far longer. There is no known mechanism to detect an impending vacuum transition. It could begin anywhere in the observable universe, or beyond it. A bubble formed a billion light-years away would still be expanding now. We would not know it existed until it reached us. There is no shield, no warning system, no survival strategy. The event does not discriminate. It does not spare complexity. It does not allow escape. Some physicists have speculated whether extremely high-energy events could trigger vacuum decay. Particle collisions, cosmic rays, artificial accelerators. Extensive analyses suggest this is unlikely. But again, unlikely is not impossible. The universe itself produces energies far beyond anything humans can create. If vacuum decay is allowed at all, nature has had ample opportunity. What makes this theory psychologically unsettling is its impersonality. There is no agency, no intent, no intelligence behind it. Reality simply changes state. The universe does not end. It continues in a different configuration, one that may be completely hostile to structure, complexity, or experience. False vacuum decay reframes the idea of cosmic safety. We often assume the laws of physics are fixed because they have always been the same within our experience. This theory suggests that stability is not guaranteed. It is temporary. We may not live in the final version of reality. We may live in a provisional one. Unlike many existential threats, false vacuum decay does not involve suffering. There is no anticipation, no awareness, no gradual collapse. One moment the universe supports atoms, chemistry, and thought. The next moment, it does not. Continuity ends without transition. If earlier theories challenge survival, memory, agency, or trust, false vacuum decay challenges something even more basic: the assumption that the rules themselves are permanent. It suggests that existence is conditional not just on circumstances, but on the continued stability of the underlying framework. The universe may appear solid, predictable, and reliable, but at its foundation, it may be resting in a shallow dip on a cosmic hillside, waiting not for a catastrophe, but for a fluctuation. The seventh theory we will cover tonight concerns the stability of matter itself. Not life, not civilization, not even the laws of physics, but the assumption that the atoms making up the world are in their most stable possible form. Strange matter theory proposes something deeply unsettling: that the matter you are made of may only be metastable, and that under the right conditions it could convert into something more stable, more compact, and utterly incompatible with life. To understand this idea, it helps to look inside the most extreme objects in the universe. Neutron stars. These are the remnants of massive stars that collapsed under gravity so intense that atoms themselves were crushed. In a neutron star, electrons are forced into protons, forming neutrons. Matter becomes unimaginably dense. A single teaspoon would weigh billions of tons. Under these conditions, the familiar structure of matter begins to break down. Protons and neutrons are not fundamental particles. They are made of smaller components called quarks. In ordinary matter, quarks come in two types: up quarks and down quarks. These combine to form the protons and neutrons that make up atomic nuclei. But physics allows for additional quark types, including strange quarks. Under extreme pressure, such as inside a neutron star, some up and down quarks may convert into strange quarks. This leads to the hypothesis of strange matter, a form of matter composed of roughly equal numbers of up, down, and strange quarks. According to some calculations, this configuration may be more stable than ordinary nuclear matter. If true, ordinary matter would not represent the lowest possible energy state of matter. It would be another false minimum, stable only because it has not yet been disturbed. A small chunk of strange matter is known as a strangelet. The terrifying implication of strangelets lies in their stability. If strange matter is indeed more stable than ordinary matter, then when the two come into contact, ordinary matter could convert into strange matter. Not through chemistry, not through burning or decay, but through direct rearrangement of quarks at the nuclear level. In theory, a strangelet would act as a seed. When it touches an atomic nucleus, it could convert that nucleus into strange matter, releasing energy and growing slightly larger in the process. The newly enlarged strangelet would then have a greater surface area, allowing it to convert more matter. This creates a runaway reaction, not an explosion, but a chain of transmutation. In the most extreme scenario, a single stable strangelet entering the Earth would sink toward the core due to its immense density. Along the way, it would convert surrounding matter, rock, metal. Everything it touches would lose its atomic identity and become part of the strange matter mass. Over time, the entire planet could be converted into a dense, inert sphere of strange matter far smaller than Earth, with no chemistry, no structure, and no life. What makes this idea unsettling is not just the outcome, but the mechanism. Strange matter does not kill life. It erases matter's ability to support life at all. Atoms cease to exist in their familiar form. The periodic table becomes meaningless. Biology does not fail slowly. It becomes impossible. Physicists have not ignored this possibility. When large particle accelerators such as the relativistic heavy ion collider and the Large Hadron Collider were first proposed, serious discussions took place about whether they could produce stable strangelets. These machines collide heavy nuclei at extreme energies, briefly recreating conditions similar to those inside neutron stars or the early universe. Safety analyses concluded that the risk was extremely small. One of the strongest arguments is observational. Cosmic rays strike the Moon and Earth with energies far exceeding those produced in accelerators. If strangelets were easily produced and stable, the Moon should have been converted long ago. The fact that it remains intact suggests either strangelets cannot form easily, or they are unstable and decay quickly. However, this does not completely eliminate the concern. Cosmic ray collisions are uncontrolled and asymmetric. Laboratory collisions are controlled, symmetric, and sustained. The conditions are not identical. The probability may be negligible, but again, not zero. Physics does not forbid stable, strange matter. It simply does not confirm it. Beyond Earth, the theory carries broader implications. If strange matter is stable, then neutron stars composed of strange matter could exist. These hypothetical strange stars would be more compact than ordinary neutron stars. Collisions between such objects could eject strangelets into space. Over cosmic timescales, these seeds could drift through the galaxy. This raises a disturbing question. If strange matter is the true ground state of hadronic matter, why does ordinary matter exist at all? One possibility is that strange matter is difficult to initiate. Another is that once initiated, it spreads slowly. Or perhaps it has already happened elsewhere. Entire regions of the universe could have been converted without leaving obvious signatures. The psychological impact of strange matter theory lies in its quietness. There is no warning signal, no explosion, no radiation burst. Matter simply changes identity. The structures that support complexity dissolve at the most fundamental level. Everything solid becomes something else. Strange matter does not rely on intent or catastrophe. It does not require intelligence, collision, or decay of physical law. It is an outcome permitted by the known behavior of quarks under extreme conditions. Ordinary matter may exist not because it is optimal, but because it has been lucky. If false vacuum decay suggests the laws of physics may not be permanent, strange matter suggests that matter itself may not be final. The atoms you trust to hold their shape may only be stable because the universe has not yet nudged them into a better configuration. The eighth theory we will cover tonight does not describe destruction, extinction, or instability in the physical world. Instead, it questions something more basic: whether the world you experience bears any resemblance to what actually exists. Interface theory proposes that space, time, and physical objects are not fundamental features of reality, but perceptual tools, simplified symbols, generated by the brain to help organisms survive. This idea comes from evolutionary biology, cognitive science, and mathematical modeling, most notably from work by Donald Hoffman. It begins with a challenge to a deeply held assumption: that natural selection favors organisms that perceive reality accurately. Intuitively, this seems obvious. Seeing the world as it truly is should confer a survival advantage. But when this assumption is tested mathematically, the results are unexpected. In evolutionary game theory simulations, different types of virtual organisms compete. Some are designed to perceive the true structure of the environment. Others are designed to perceive only information relevant to survival, ignoring underlying reality. Across thousands of simulations, the organisms that perceived the truth consistently lost. They were slower, less efficient, and more computationally burdened. The organisms that survived were those that perceived simplified signals tied directly to fitness. The conclusion is unsettling. Evolution does not reward truth. It rewards usefulness. Accurate perception is costly, Processing the full complexity of reality requires immense computational resources. For survival, this is unnecessary. An organism does not need to know what an object is made of. It needs to know whether it is safe, dangerous, edible, or irrelevant. As a result, perception evolves not to show reality as it is, but to hide it behind a user interface. Interface theory uses a technological analogy. A computer desktop displays icons, a brew folder, a trash bin, a document symbol. These icons are not the computer's internal structure. They do not resemble transistors, voltages, or binary code. They are simplified representations that allow effective interaction. If the computer showed its true internal state, it would be unusable. The interface lies, but the lie is functional. According to interface theory, space and time function in the same way. Objects, distances, and motion are icons. They are not fundamental components of reality. They are representations generated by the brain to guide behavior. When you see a chair, you are not seeing the underlying structure of reality. You are seeing a symbol that means something that can support weight. The symbol feels solid, continuous, and objective, but it is not a direct window onto what exists. This reinterprets physics in a disturbing way. Under interface theory, physics does not describe the true nature of reality. It describes the rules of the interface. Equations about particles and forces are not maps of the underlying world. They are regularities in the symbols our interface produces. Measuring smaller scales or larger distances does not break through the interface. It only reveals more structure within it. Quantum mechanics, in this context, looks less mysterious. At very small scales, physical objects behave probabilistically. Particles do not have definite positions until measured. Observation appears to affect outcomes. Under interface theory, this is not because reality is strange, but because the interface is reaching its limits. Like zooming in on a digital image and seeing pixels, quantum effects may represent the resolution limits of perception. This also reframes the role of the observer. Consciousness does not sit inside space and time. Space and time exist inside the perceptual framework of consciousness. What lies beneath that framework is not spatial, temporal, or object-based in any familiar sense. Interface theory does not specify what reality is made of. It only claims that it is radically unlike what we perceive. The unsettling implication is that we are not gradually discovering the true nature of the universe. We are refining a user interface. Telescopes, microscopes, and particle accelerators extend the interface, but they do not remove it. They add detail to the symbols without revealing the underlying structure. Reality remains hidden not because it is distant, but because evolution selected against seeing it. This theory does not suggest that reality is imaginary. The interface corresponds to something real, just as a desktop icon corresponds to a real file. But mistaking the icon for the thing itself leads to error. Space may not exist. Time may not flow. Objects may not persist independently. These may be conveniences generated for survival, not features of the underlying world. The psychological impact of interface theory lies in its quiet erosion of trust. If perception is not designed for truth, then certainty becomes fragile. The world feels solid because the interface is consistent, not because it is accurate. What appears fundamental may be provisional. What feels obvious may be deeply misleading. Interface theory does not end the world. It leaves it intact, but it changes its status. Reality becomes something we are shielded from, not something we are gradually uncovering. We are not explorers approaching truth. We are users interacting with a surface, unaware of what lies beneath it. The ninth theory we will cover tonight proposes something quietly destabilizing. That reality itself may not be fundamental. The simulation hypothesis suggests that what we experience as the universe could be an artificial environment generated by an underlying system, one that exists outside the space and time we perceive. The idea begins with a simple extrapolation. Technological progress tends to increase computational power. If a civilization survives long enough, it may reach a point where it can simulate environments in extreme detail. Not simple games or models, but entire worlds populated with conscious agents. If such simulations are possible, and if advanced civilizations create many of them, then simulated minds would vastly outnumber original biological ones. From a statistical perspective, this leads to an uncomfortable conclusion. If most conscious beings exist inside simulations, then any randomly selected conscious observer is more likely to be simulated than original. The fact that your experiences feel real does not help. Simulated experiences would feel just as real to the beings having them. Consciousness does not require a base reality. It requires structure and process. What makes this idea unsettling is not the presence of creators, but the loss of grounding. If reality is simulated, then the laws of physics may not be fundamental. They may be constraints imposed by the simulation. Constants that appear finely tuned may not be mysterious at all. They may be parameters chosen for stability, interest, or efficiency. The universe may look the way it does because it runs well that way. This reframes many deep questions. Why does the universe have a maximum speed? Why is information quantized? Why does space-time appear pixelated at the smallest scales? Under the simulation hypothesis, these are not cosmic necessities. They are computational limits. Resolution, bandwidth, update rates. The theory does not require the simulators to care about us. They may be long gone. The simulation could be automated. It could be archival. It could be running for reasons unrelated to observation. There may be no monitoring, no intervention, and no concern for what happens inside. The system simply executes. The existential discomfort comes from fragility. A simulated world can be paused, altered, or terminated without warning. There is no cosmic obligation to continue it. No appeal to natural law for protection. Existence becomes contingent not on physics, but on an external decision or system state. Even worse, evidence becomes suspect. Any observation consistent with simulation can be explained as part of the simulation. Any observation inconsistent with simulation can also be explained as a design feature. Like Boltzmann brains, the hypothesis is difficult to disprove from the inside. The tools used to test it are part of the environment being tested. The simulation hypothesis does not require deception. It does not imply that reality is fake. The experiences are real. Pain is real. Meaning is real. But the foundation beneath them is no longer secure. The universe becomes a constructed space with an off switch. If quantum immortality traps consciousness in survival and interface theory hides reality behind symbols, the simulation hypothesis removes final authority. The universe is no longer the ultimate context. It is a container. And containers can be closed. The 10th and final theory we will cover tonight concerns the ultimate fate of the universe, not through catastrophe, but through inevitability. Heat death is the conclusion drawn from the second law of thermodynamics. Entropy increases. Energy spreads out. Over time, usable energy is consumed, and differences that allow work to be done disappear. The universe runs on gradients, hot and cold, dense and sparse, high energy and low energy. Stars shine because there is a difference between nuclear fuel and empty space. Life exists because energy can be harvested and directed. Thought itself depends on physical processes that require free energy. When those gradients vanish, complexity follows. As the universe ages, stars burn through their fuel. Star formation slows. Galaxies darken. Eventually, no new stars ignite. Existing stars fade into remnants. Black holes dominate. Over unimaginably long timescales, even black holes evaporate through quantum effects. Matter thins. Energy spreads nearly evenly across space. In this final state, nothing dramatic happens. There are no explosions, no collapse, no end signal. The universe simply reaches a condition where no further meaningful change can occur. No work can be extracted. No structures can be built. No processes can sustain complexity. Time continues, but nothing happens. This is what makes heat death uniquely disturbing. It is not violent. It is absolute. Once reached, there is no mechanism for recovery. Entropy does not reverse on cosmic scales. The universe becomes a vast, cold equilibrium, filled with particles drifting endlessly, unable to interact in any way that produces novelty. From the perspective of consciousness, this represents a hard boundary. Thought requires energy flow. Memory requires physical change. Awareness cannot persist in equilibrium. There is no quantum trick, no technological intervention, no expansion strategy that defeats the second law forever. At best, complexity can be delayed. It cannot be preserved indefinitely. Some theories propose escapes, cyclic universes, new physics, multiverse reproduction, but none are confirmed. Heat death remains the default expectation given what we know. Not because the universe is hostile, but because it is impartial. The unsettling aspect of heat death is that it removes narrative. No final battle, no climax, no transformation.